All right, everyone. So we're going to start section 10.3. Again, this is Nick Jacobs, your intermediate algebra instructor here at Yavapai College. 10.3 is on simplifying radical expressions. So a few objectives, or just a couple really, but quite a bit actually to handle. So we're going to apply the product rule of rational expressions. I keep saying rational. We did that last section, radical expressions, and apply the quotient rule for radical expressions. So first off is the product rule. Okay, and I kind of gave this example. So if I have something like the square root of 4 times the square root of 25, I know that I can have that the square root of 4 is a perfect square. That's 2, the square root of 25 is 5. And both of those multiplied together equal 10. Well, I can also do this. So I could take these two things and I could put them under one radical to have 4 times 25, multiply 4 and 25, and that gives us 100, and the square root of 100 is 10. So we get the same thing either way. And that's kind of our product rule. So these two things mean the same thing. If I have the square root of n, if I have root n of a times root n of b, that equals root n of a times b. But again, a and b have to be real numbers, and these have to be defined. You won't run into any, I won't try to trick you at all in that, so don't kind of worry about that. But note that this product rule here only applies if they have, if the radicals have the same index, okay? So they have to have the same index n. There is one exception, which I will kind of talk about here in a little bit. And that's kind of when you could have a different index, but the same exact radicand. So here, a and b are not the same. But there is that exception where if it's, if both of them are a, but your roots have a different index, then we can do that. But let's just talk about some examples here. Again, the only way to kind of do this is to go through examples, do examples, and if you have questions, let me know, or there's always the Learning Center, right? So first example is the square root of 36 times the square root of 4. And again, oops, kind of what I don't know why it just wrote that line. What our product rule tells us here for radicals is that we can take the 36, multiply it by the 4, and that gives us the square root of 144 using a calculator there. And then that equals 12. Okay, so 12 is the answer here. But again, what you could do is you could do this separately. So I could have done the square root of 36, which is 6, and then the square root of 4 is 2, and that also gives us 12. So either way. And then again, you can kind of choose what way is going to be the quickest for you. This one, it might be quicker to do what we did here, but I'm going to do it sort of the longer way to start off with. So again, I can combine these here. This is a cube root this time. I keep the index, kind of like I did here, and then I multiply what's inside. So I can do the -8 times the 27. And that gives us, I actually had to write that one down. I don't know that. That is -216. And then that is actually a perfect cube as well. So, in this case, so that gives us -6. And this one, because both -8 and 27 are perfect cubes, I could have done this. I could have just done, well, the cube root of -8 is 2. Cube root of 27 is 3, multiplied those together and got the -6 again. But in example C here, we can't really do that because the 4th root of 1/4 is not a perfect root. Neither is 4th root of 1/16. So what I have to do here really is I have to multiply all of these together. But again, what I can do is I can take each radicand here and write it under one radical, okay? And then I can multiply, if you kind of recall from basic math, before algebra, multiplying fractions, you multiply straight across the top, straight across the bottom. So the 1 times 1 times 1 is 1. 4 times 16 times 4 is 256. And then we'll actually learn the quotient rule, which says that I can actually break these up into the fourth root of 1 divided by the fourth root of 256. But for now, this guy, the 1 over 256, is actually a perfect fourth root. And you guys can write that on your calculator or type that in, but that's 1/4. And again, I'm not showing you, as I mentioned in previous videos, I'm not showing you the calculator steps because you all have different calculators. If I was, no, not all of you, but there are different calculator variations. So if I were to show you something on my calculator, you might be confused with the steps on your calculator. So there's always the resource of Google, right? Google has almost everything, or YouTube. If you don't know how to type in the fourth root of 1 over 256 on your calculator, YouTube it, Google it, and there should be some kind of video based on your version of your calculator. If you still can't figure it out, please let me know, and I will help you out with your calculator version. The last example is D, and I kind of threw this one in myself, but the point is here is that, look at this, the indexes are different. So what does this mean? This means we cannot multiply it. So we cannot simplify this any further. Okay. Cannot simplify because the indexes are different. They're not equal to each other. And again, if this was the, I'll just write it up here, the cube root of 11 times the fourth root of 11, then yeah, this is an exception. This is an exception here that I could take this and we could use something like we did last section. We could take this 11 and we could put it to the 1/3 power. You guys remember that from 10.2. And we could take this one and put it to the 1/4 power. And then I could, well, when I multiply with the same base, we learn that we add the exponent. So I could actually do the 1/3 plus the 1/4 here, which would give me, let's see, 1/3 is the same thing as 4/12. I'm getting a common denominator. 1/4 is the same thing as 3/12. 4/12 plus 3/12 is 7/12. So this would be 11 and 7/12 as their exponent, or the other way to write that. This is generally how your homework would want it written in kind of that rational form for your exponent. But we could also write it as the 12th root of 11 to the 7th. And you could, I guess, simplify 11 to the 7th, type that on your calculator, but I'll just leave it like that. So I will do another example of this exception later, but generally, if you have different indexes along with different radicands, you cannot multiply. You can't simplify that. All right, let's do some examples now with variables. So multiply each radical expression. So if I have the square root of x squared times the square root of x to the 4th, again, what I'm doing is I can combine these, okay, two things. I have the same index, right? It's a 2. They don't always write the index, right, of 2 if you have a square root, but it is kind of, it's there. And then I could, combine these, right, by adding, right? We do 2 plus 4. Don't get that confused. Some people would put an 8 there, but it is x to the 6th. And then you take the square root of x to the 6th. That is a perfect square there. And when you have the 6 there and the square root, that's x to the 3rd. The other way to do it, again, would be kind of what we talked about last time, is writing these with a rational exponent. So we have x to the 1/2 instead of the square root of x squared, and then x to the 1/4, right? And kind of actually, why did I just, that's not what I meant. I don't think that's what I meant anyway. No, I can't do that this way. I know I did it with the 7, but that was different because that was this guy. I'm completely off here. in what I'm doing. The 2, it should be x to the 2 over 1 times x to the 4 over x to the 2 over 2 times x to the 4 over 2. That's what I mean. Okay, so you could do it like this. And then, oops, that's a 2. This would be x to the first times x to the second, which we do the 1 plus the 2, which is x to the third. So that's kind of another way to do it. I don't really recommend this way. I mean, I did it with the 11 over here on the last slide, but you know, you could do it like that. Again, I can write it as 2 over 2. This is an index of 2. This is an index of 2. I can write it as 4 over 2. Sorry, I was thinking back to the kind of the last question with the 11, where it had a power of 1, right? It had a power of 1. And really, for your notes, if you're looking at this, just your notes, I don't want to write that 1 in there, but just kind of making an emphasis here. And maybe some of this is too much, okay? And you can just kind of read the notes, but I'm trying to, I know this can be a little confusing, and I'm trying to give you as many kind of examples as I can think of. The next one is the cube root of 5a times the cube root of 10a squared. So again, same idea here. I'm going to use the product rule to combine these. So I'm going to take the 5a and multiply it by the 10a squared. And that gives me 50a to the third. Well, cube root of 50 is not a perfect cube, so I can't do anything with that. But the cube root of a cubed is a perfect cube, so I can take that a out of there. So that would be a times the cube root of 50, and that's the answer. And then this one, okay, so we have a 4th root. Again, I can multiply right straight across the top. I can go 3x times 7y over y times x. I'll just switch them around, x times y. And then what I can do, okay, let's just combine. So 3x times 7y, yes, I can multiply those. That would be 21xy over xy. But then look what happens. These, this x cancels and the y cancels. And I'm really just left with the 4th root of 21 over 1. I would just write it as the 4th root of 21. So, and I'll talk about this here in a second, but it's really, really beneficial for you guys to know perfect squares, perfect cubes. And I think we're going to talk about that here in a little bit. But the next thing is simplifying radicals or nth roots, okay? So I have a kind of a couple steps here. Step 1 would be to determine the largest perfect nth power factor of the radicand. Step 2, use the product rule to factor out and simplify this perfect nth power. I'm not really going to refer to these steps, but I'm going to do the examples. You can refer back to the steps. I'm not necessarily a step kind of person. Okay, it's hard enough, I think, to remember what to do with letters and numbers than to also throw words into that. But if you're a step person, you know, you can definitely do that. So here is where I kind of say, yeah, it's really beneficial, you know, if you know some of these perfect squares, okay? So if you know the square root of 1 is 1, the square root of 4 is 2, square root of 9 is 3. This is a 4, by the way, that's a 4. 16, square root of 16 is 4, square root of 25 is 5, etc., right? And then also to know perfect cubes. So the cube root of 1 is 1. The cube root of what makes a 2 here? Well, it'd be 8, right? The cube root of 27 is 3. The cube root of what makes a 4? 4 cubed is 64. And then the cube root of 125 is 5. We could keep going, right? The cube root 216 is 6. And if you want to keep going with that, okay, but it's really beneficial to know those perfect squares, perfect cube, things here. So simplify the expressions. Square root of 500. When I'm thinking about this, okay, let me do an easier one for you. Okay, let me go back. Did we have the square root of 12 earlier? I don't know. Maybe not. But if we have the square root of 12, okay, I'm trying to think of breaking this down, kind of using your product rule. Think of think of a perfect cube, right? Think of how can you break down 12 into factors where one's a perfect cube and maybe one is not. Well, it would be 4 times 3, right? 4 times 3 is 12, but the square root, maybe, did I say perfect cubes before? I don't know. I'm sorry if I confuse you. Perfect squares, right? We want perfect squares. So the square root of 4 is 2. And then I just have the square root of 3 left over. So that would be 2 square root of 3. Now here, again, you're thinking of, okay, can I make a perfect, or can I have a factor of 500 that's a perfect square? And yes, 100, right, times 5 is 500, and the square root of 100 is 10. So yeah, I can do that. And then this is just 10 times square root of 5. So that is it there. Now, you might think, well, what if I couldn't think of that? What if I thought, maybe 25, right? Or maybe just 10. Okay. Well, that's okay. So if you broke 500 into, 10 times, well, not 10, because the square root of 10 is not a perfect square there. But maybe, like the square root of 25. What's 500? Let me do it on my calculator because my brain is not okay today. No, I'm just kidding. Square root of 25 and then 25 times 20. So what if you did that? Okay. Well, that could work. Okay. Well, the square root of 25 is 5, and then the square root of 20. But the only thing is that the square root of 20, I can still go a little bit further, right? So I could do that as square root of 4 times the square root of 5, right? 4 times 5 is 20. And then I know the square root of 4 is 2. And so I can take that 5 times 2 and get the 10. Okay, but just another way to do it. So if you can't think of it, right away, kind of the fastest way to do it, break it down and see if, you can still break it down later, and you can do it like this. Now the cube root of 40. So think of factors of 40. So remember we did our factor trees earlier, 2 and 20. What else makes, so that's 2 and 20. What else makes 40? 4 and 10. I don't know why it keeps doing that little bar above the 4s. I apologize for that if I'm confusing you. Maybe you think that that's a 9 or something. That's a 4. And maybe 5 times 8. Oh, 8. 8 is one of our perfect cubes, right? So I can take this cube root of 8, and I'm always going to kind of write that perfect, square, perfect cube one out in front, and then multiply it by the one that's not. And that's only because when I simplify this, I'm going to want that whole number without the radical out in front anyway. That's just the proper way to write it. Like in this, I would never write square root of 5, 10, and then at the end, I would always write the 10 out in front. Same thing here. So I know that the 8 times 5 is 40. Cube root of 8 is 2, and then I cannot simplify the cube root of 5 any further. So this is as far as this one goes. Again, the 2 is going to go out in front. Square root of 72. Again, if you're not good at your perfect squares and whatnot, that's where a little bit of practice comes in. But I know that 36 times 2 is the same thing as 72. The square root of 36 is 6, and I can't break down the square root of 2 anymore. So that one is simplified. All right, we're almost on to our quotient rule. It's just taking a little bit longer than I thought. But let's try to simplify some of these, kind of a little bit more mixed with your numbers and variables. So I have the square root of 49 times x to the fourth. And again, we're just assuming all variables are positive, so we don't have to worry about that whole absolute value thing that we talked about a few sections ago. But here, what I can do is, again, kind of use that product rule to split this up if it helps. Okay, so I could split this up into the square root of 49 times the square root of x to the fourth. I did it again with that little line above the 4. And anyway, again, the square root of 49, that's a perfect square there, that's 7. And then the square root of x to the fourth is x squared. So it's just 7x squared simply. And, you know, if you know that kind of right away, you don't have to write this out separately, but I'm just going to showing you that. And then this one, square root of 75 y to the fifth. Now, this one is a little bit trickier. There's several different ways to do this one. I'm just going to kind of do it first how I did the last one. I'm going to break it up, okay, into two different radicals. And then if you want to, you can kind of, you know, take the square root of 75, okay, break it up. So it's square root of 25 times the square root of 3. You're probably like, oh, he picked 25 because it's a perfect, you know, perfect square, right? You know, square root of 25 is 5. Okay, so I have 5 square root of 3. Then y to the fifth, that's the same thing as y to the fourth. Oh, this is going to drive me crazy, guys. Why this keeps putting this line up here, I don't know. This is y to the fourth times y, right? 4 plus 1 is still 5. And then the square root of y to the fourth is, in fact, y squared. And I can't break down the square root of y anymore. It's already simplified. And I can take these two guys and combine them. So I can have 5y squared and then combine what's in the radicals by that product rule, right? Same index. I can still multiply those together, 3 and a y. So I have 5y squared times the square root of 3y. Now, the other way to do it, and this is maybe, you know, the way that the book would do it, and, you know, maybe they're just a little more advanced than me, but they would go ahead and they would say, oh, well, I can take out a 25y to the fourth. 25y to the fourth. And then I can kind of multiply that by 3y. Okay, so what's in there in this radical does multiply together to give us 75y to the fifth. The reason they did that is they said, oh, this thing in parentheses, that's a perfect square. So I can take out that 5y squared right there and then, you know, times it by the 3y and still get the same thing. But, you know, if you don't see that right away, you can kind of do some of these longer steps here. So let's go ahead and do this last one. This is C. So again, I can use this product rule, multiply what's inside here. I'm going to multiply the coefficients, 3 and 9, it's 27. A and a squared would be a to the third, right? I do the 1 plus the 2 because I'm multiplying. And then W. And then in this case, you know, for me, this one's easier to see. You know, I can see here that, you know, the 27a cubed is a perfect cube. There, I can take that outside the radical. It's just a 3a. And then times the cube root of W. So that's how we do that one. Again, I think this one is easier than this one, but you be the judge. Okay, couple more examples, then we'll get into the quotient rule. So this is kind of what I'm talking about. This is that exception where you have an index right here of, you know, nothing. Well, not nothing, but it's 2, and then the other index is 3. Okay. So you can multiply these together in this case because the radicands, the 7s, that is, are the same. Okay. So in the way we do that is we're going to rewrite this as 7 to the 1/2. Okay, because this is a 1, and then your index is 2. And then this one would be times 7 to the 1/3, okay, because the 1 and the 3. And then again, when we multiply with the same base, different exponents, we add the exponents. So 1/2, not times 1/3, but plus 1/3. And we know 1/2 plus 1/3, if you're not good with your fractions, type it in on your calculator, but that's 7 5/6. And you're probably like, well, can I write that in any different form? And the answer would be maybe. I think this is how your MyLab is going to want it on the homework if you have a question like this, but you could, yes, also write it as the 6th root of 7 to the 5th, okay, which is the same thing as if we would take the 7 to the 5th. What did I say? That's 16,807. So I'm gonna, say write it this in this form, and MyLab might tell you to write it in that form, but if they don't tell you, this form or maybe this could also be correct. And this one is kind of the same example, just with we have a radicand here of a, so it's just a variable. So I could write this as a to the 1/3 times a to the 1/5. And then again, we are taking the one that's a 1/3 plus the 1/5, which is, well, let's see, this is the same thing as 5/15. And this is the same thing as 3/15, right? Times by 3, times by 3, times by 5, times by 5. 5 plus 3 is 8. So it's a to the 8/15. And again, yes, this form is also correct in my book, but MyLab might want something different. Okay, let's try to finish this up with the quotient rule. So again, consider the following. So if I am dividing radical expressions, so if I have the square root of 4/9, I could break up 4/9 as the square root of 2/3 times 2/3, and then take one of those 2/3 out, right? But I could also break it up like this. So I could say that I have the square root of 4 in the numerator divided by the square root of 9 in the denominator, and then simplify those two from there. So the square root of 4 is 2, the square root of 9 is 3. These mean, and these are kind of the same thing. But our quotient rule here is really that I can take this guy and split it up into two different things, or I can take these two different things and go the other way. I could put it in one radical. And we'll kind of use both things here. And again, always b cannot equal 0, because that would make it undefined, as we've talked about before. So let's go ahead and try this out. So simplify each radical expression. Again, assume all variables are positive. So again, let's use our quotient rule. And what we do is we break it up like so. This is what it says. I can take the numerator, put it up there, take the denominator, put it down here with the index of 3. Now the cube root of 7 is not a perfect, cube, but the cube root of 27 is, and I know that that's 3. This is fully simplified. Okay, this is what they mean. Now this does get a little interesting when we have a radical in the denominator. We would have to do something called rationalizing the denominator, and we will talk about that here in upcoming sections, but you don't have to worry about that here. These are all just going to kind of work out pretty well. So let's do B, and I'm already doing it. We're going to split this up like so, according to our quotient rule, and then we have the 5th root of x. The 5th root of 32 is a perfect root. It's just 2. Right? Because 2 to the 5th is 32. And that's as far as you can go. Okay, let's keep going. Now this is kind of going the other way. These are the ones that we're using the quotient rule, but we're actually combining these two things. So I'm going to combine this as 90/10. And the reason for that is 90 divided by 10 is 9. Oh, the square root of 9 is 3. Okay, so that one is done. I can kind of use this as almost like the backwards quotient rule. And the same thing with this guy. I'm going to combine this as one radical, x to the fourth over y, or sorry, x to the fourth times y over y. And then the y's would cancel out. So I'm left with x to the fourth, and the square root of that is actually a perfect square. That's x squared. All right, kind of trying to go quickly and finish up. Simplify the radical expression, assume that all variables are positive. So again, here we have the fifth root of 32x to the fourth over the fifth root of y to the fifth. This is one where, yeah, it's written as one thing. You're going to kind of want to break it up into two different things to make it easier for yourself. So we have the fifth root of 32x to the fourth over the fifth root of y to the fifth. And again, that's the quotient rule. Now, the fifth root of 32x to the fourth. Well, the 4 is less than the 5, so I can't do anything with the x to the fourth. Okay, if it was like an x to the sixth, then yeah, I could take out an x. Or if it was x to the fifth, I could take out an x perfectly in that case. But in this case, 32 is a perfect fifth root. And to just kind of demonstrate that, I am going to break this up using our product rule for the numerator at least. And then kind of take these separately. So this is y. It's a y to the fifth. Fifth root of 32 is actually 2, as we said before. 2 times fifth root of x to the fourth over fifth root of y to the fifth. That's just y. And that is all you can do for that one. Okay. Now, a couple of slides to finish up here. These are optional, okay? Because they won't be on your homework at all. They won't be on a test. But if you are interested in these types of problems, you know, maybe you're going to go on to another math class after this, like pre-calculus. You know, you will do this kind of stuff in pre-calc. So I'm showing you these examples, not because they're required for intermediate algebra, but because they're good to know for other math classes. So we have a radical expression now inside the radicals. I can still use the product rule when our index is the same, okay? So I can still take this as x minus 1 times x plus 1. I can combine it, okay? And I could FOIL that out, and I'm not going to do all that, but that's going to give us x squared minus 1, right? Remember, this is a difference of squares. Kind of recognize that. And that's actually as far as you can go. Okay, that is simplified. Because I can't take any of these out. All right. I can't take out the x squared. All right, the square root of x squared is x, but it's minus 1. So, you know, doing this incorrectly, some people would do it like this. The square root of x squared minus 1 is not equal to the square root of x squared minus the square root of 1. Those are not the same thing. Okay. So don't get confused in that. But, you know, I could say something like this. So I could say, well, let me try to find like an example. The square root of, let's say, 25 minus 16. Actually, okay, I'm not going to do it. This is optional. Just know this is not the same. Okay, especially when you have that variable in there. Oops, and I actually wrote down this. I forgot to delete one of those steps. Or I was gonna keep doing that. But I think I did it for this one too. So this is the same question. Now what we can do here, again, this is optional. The cube root of x squared plus 5x plus 6. Well, what I can do there is I can factor that out. So that actually factors into x plus 2 times x plus 3. Okay. And that's over the cube root of x plus 2. Well, I can write these two in the numerator separately. And then I have the cube root of x plus 2 in the denominator. These things you can cancel, okay? So I'm just left with the cube root of x plus 3. So that's not too difficult, I don't think, but we aren't going to get into it for your homework. I just wanted to show you that example. So That is it for section 10.3. We're going to do more with radicals next time in 10.4. And until then, I will see you later.